Hello. In this video we're going to be going over the slides for Chapter 7 in the second edition of the Top Hat book. So for the previous book, these were separated into Chapter 7 and 8, but they have combined them in the second book. We're going to be going over SN1 and SN2 reactions. Today we'll talk about the first real reactions in the series. So the first one we're going to talk about are the substitution reactions, and they're called SN2 reactions because it stands for they are going to be substitution reactions. They're going to use a nucleophile to do that, and we'll talk about that means in a minute. And they're bimolecular, so they have two chemicals coming together, two starting materials coming together in the rate determining step. Okay? And so the nucleophile, if you remember, is actually, so let me get this going. So the nucleophile, remember this is the nucleo, is the same prefix as nucleus, right? So if you are a nucleophile, you are positive phile loving. So if you're positive loving, that must mean that you have negative character to you. In contrast, if you are the electrophile, so electro, in the same root as electron, right? So this would be negative loving. And so you are ultimately going to have positive character to you. Okay? And within that electrophile, okay, we're going to have what's called a leaving group, and that is going to, its sole purpose is to leave, and with it take electrons with it. Okay? Because typically what happens is the nucleophile is going to be reacting to a carbon that's either that is part of a polar covalent bond. The carbon can't have a fifth bond, so it needs to get rid of one, and the easiest thing to do is to push those electrons onto the leaving group. Okay, and so the nucleophile will then substitute for where that leaving group was. Okay. And so for the mechanism of the SN2, the basic mechanism is what's called a backside attack. Okay, and so for figuring these things out, typically what you want to do is, first thing to do is to look at the, figure out the nucleophile, and it's going to have negative character. It doesn't have to necessarily have negative charge, but it's a good, we'll talk about what makes a good nucleophile a little bit later in the chapter. But for here, this is going to be our nucleophile. Okay, so it's going to be searching out a positive charge, or at least something with positive character. And so what we need to do is we need to look for the polar covalent bond. Okay? And so this sulfur, right, it's going to be attracted to that partial positive. And so what it does is it comes in here and it uses its lone pairs to make a new bond to that carbon. Okay, the negative is going to get attracted to that positive. And in doing so, this carbon can't have 5 bonds, right? So what it needs to do is it needs to start pushing these electrons onto the most electronegative atom, which is going to be our leaving group. And so as this nucleophile comes in, it's got to push these the other 3 groups that are on the carbon away so we can get access to that carbon. And in doing so, we're going to be breaking the bond between the carbon and the bromine, and so you're going to end up with this. And so these original lone pairs here turn into the 2 electrons of this bond. Okay. The 2 electrons within that bond become this new set of lone pairs here. So you're going to see this a lot of lone pairs going to bonds, bonds going to lone pairs, electrons. Okay. And if you do the formal charge on the bromine, now it has a negative charge. The mechanism, okay, so we have everything's going to happen all in one smooth motion. As the so you have the reactants here, as the sulfur's coming in, okay, you're breaking the other bond, the carbon bromine bond. That's going to cost you energy, right? As well as pushing the hydrogens out of the way. Okay, that's going to you're going to have to spend a little money, and after you push that away, you create your products. Okay, but again, you're gonna have that transition state where you've got a lot of energy, but overall you're going to be working out well. Just like you have to spend $1 on a scratch-off ticket in order to be able to win $5. So you got to spend a little money to make a little money, right? You got to spend some energy in order to be able to be better off overall. Now, this happening all in one smooth motion are what are called concerted reactions. Okay, that means there's no intermediates. Everything happens all in one smooth motion. Okay, so this coming in, this breaking, no intermediates. Okay, and so when you see that, it's called a concerted. The reaction's concerted. Okay, and so remember, one of the ways that we have to do this reactions is saying, like, in order to be able to get over that activation energy, okay, you have to have some sort of threshold, right? If you're trying to take your bike over a hill, right, if you don't have enough energy, right, you're not going fast enough, you'll just roll back down that hill. Okay, but eventually, if you get enough energy, you'll be able to get over that hill. And so this is the activation energy. So this is the minimum energy to get over that hill, so you can keep going down the other side. Okay, so at lower temperatures, there's only a small portion of it down here. Only a small fraction of those. Well, here, let me do it in a better color. A small fraction of the total molecules will have enough energy to be able to do that, right? Because remember, temperature is just the average kinetic energy of the system, right? But if you heat it up, if you heat up the system, okay, what you're doing is you're giving those molecules more energy, and so now it's going to widen this distribution, okay, and so now you're going to have a much larger proportion of your molecules to be able to have enough energy to be able to get over that, right? And so that's why heating a reaction typically makes it go faster. Now there's other issues, okay, because then alternate pathways, so you have to be careful because it may have enough energy to do other things, right, to do side reactions, something like that. But generally what's going to happen is if the reaction's going slowly, the best thing to do is to just heat it up. And the reason why that works is because you're giving it enough energy to get it over the activation energy. Okay, so if you think about the kinetics of this, okay, we're not going to do really we're going to talk about calculations or anything, but the kinetics will tell you why it's an SN2, okay? Remember, there's really only one step, okay? So that one step is going to be the rate determining step, and that rate determining step requires both starting materials. So it requires the electrophile here as well as the nucleophile, the OH minus. Okay, so the rate is going to be proportional to some constant that you look up in the big book of reaction rate constants, times the concentration of your electrophile, or excuse me, nucleophile times concentration of your electrophile. Okay, and so because there's two components in that rate determining step, both of those can make a difference to the rate. And so one of the ways you can figure out if you're running under SN2 or SN1, which we'll talk about in a minute, is just changing the reaction rate, okay? And so if you are running at, so this would be 1 millimolar electrophile and 1 molar nucleophile, right? You're going to get some base rate, 4.9. If you keep the nucleophile the same, but you double the the electrophile rate, right? Now you're running it twice. Right, so if the rate, so if you're running at, right, K time, right, K time, 0.001 times 1, right, that'll equal, 0.001. If instead you double, right, this concentration, right, it's going to be 0.002, whatever, right, you're going to be 2, it's going to equal 0.002 K, right, this should be K, right, you're doubling the rate, right, because you're twice as likely for them to smash together, right? If instead you doubled the nucleophile instead, you would also double the rate if you held the first one constant. But if you double both, right, look at it here. Right? So rate is equal to k times 0.002 times 2, right? Now you're at 0.004k. So if you double both of them, right? So if you double this one and double this one, 2 times 2 is 4. So if you double both of them, you don't double the rate, you quadruple the rate. Okay, so that's what this is going after. Okay. Now with the stereochemistry, so one of the things that happens is because it has to, what we call a backside attack, this nucleophile is going to want is interested in approaching as close as it can to this partial positive, right? It doesn't want to get near the partial negative, right? Because negatives attract, right? Just like if you try to put two north magnets together, right? They're going to repulse. But if you put a north and a south together, they're going to snap right together. So it's going to approach what's called from the backside. And in doing so, it's got to remember all of these black groups here. That's got to push those out of the way. And the visual is to think about if you're walking with an umbrella and a gust of wind happens, comes up, boom, your umbrella is likely to invert, right? Go flook, and now you're all wet. That's what happens here. Those groups invert, and in doing so, okay, by pushing them over to the other side, you actually invert the stereochemistry. So if your starting material, if your electrophile was R, okay, your product is going to be in the S configuration. So the and if you were started with the S, it would be the R. Okay? So the way to think about this is to say, okay, if your leaving group is say on a wedge, well then the nucleophile when it comes in, remember the wedge means it's coming out at you. So it means the leaving group is coming out at you. So because it needs to come from the back side, that means the nucleophile has to come from underneath. And so when it attaches to the electrophile, it's going to be pointed in the opposite way. So if your leaving group is on a wedge, that means the product is going to have the nucleophile on a dash. Okay, so if we're looking at this one here, right? So so here's the nucleophile. Right, because it has the oxygen with a negative charge. It's pretty nucleophilic. Okay, so that means the other molecule must be the electrophile. So for there, we're looking for a polar covalent bond, and for that, it's right here, right? Because all the rest of them are either carbon-carbon or carbon-hydrogen bonds. Those are essentially all covalent. So what's going to happen is one of these lone pairs, right, is going to get attracted to that carbon because that's where the positive charge is. But it's going to come in from the top, right, because the bromine is pointed away from you. And so when that pushes away, right, what you're going to get is the nucleophile. Because the leaving group is on a dash, your nucleophile is going to be on a wedge. Okay. Plus Br minus. Okay. Now, nothing happened between this carbon-oxygen bond. Okay, so the whole thing comes in and just bolts right in. Okay. So here's our full nucleophile, and we're going to attach. And so all we did was use one of these sets of lone pairs on the nucleophile to make a new bond to that carbon. Okay, the two electrons on the dash there became this new set of lone pairs here. Now for this one below, right? So again, this is going to be the nucleophile, right? Because sulfur's a pretty good nucleophile with a negative charge. So that means we're looking for the polar covalent bond on the electrophile, so it'd be here. And so we're going to be wanting to attack here, push this away. And so since the leaving group, right, the chlorine is pointed towards us, we have to come in from behind. And so that means our nucleophile is going to be on a dash plus Cl. Like that. Okay. There we go. Now, remember for nucleophiles, right, we're going to have negative character to them. So they can have, typically they're going to have negative charges. Okay. But that, although they could be they could have a partial negative. Okay, they don't necessarily have, they just have to have negative character to them. Okay, and so if you're part of a polar covalent bond here, here and here. So for these guys, so these organolithium and the organomagnesium ones, you can sort of think about this as being a stabilized carbanion here, right? Because carbon's more electronegative than either lithium or magnesium, so they're going to want to stay onto the carbon. Okay. So for that, but you can have the negative part of a polar covalent bond. Okay, so that can also be nucleophilic. The other one that kind of messes people up, or or I should say people forget, is between a double bond. Okay, because remember right here we have 4 electrons shoved into a between 2 carbon atoms. There's a lot of electron density there, and so it can act like a partial negative charge, and that's going to have negative character to it, and so we can use that to do chemistry. We'll see that in a couple chapters. Now for electrophiles, right, so they're going to have positive character to them, and so they're usually either going to have a fixed positive charge, or they're going to be on the positive side of a polar covalent bond. That's usually what ends up being. You can also technically have a lot of metals, right, because they're going to have positively charged. Those would also act as electrophiles as well. So some work better than others. Now, so if you're looking at this, okay, so if you're trying to figure out if this is a nucleophile electrophile, right, what you're going to be looking for, right, is a polar covalent bond. So for this one here, right, we have this carbon-nitrogen bond, right? Nitrogen is more electronegative than carbon, so that must mean this is it's a negative, that's a positive, right? So since it's negative character, that must mean it's a nucleophile. For here, this carbon here, polar covalent bond right there. Okay, and so again, this is partial positive, partial negative, right? Because bromine's more electronegative than carbon is. So this carbon is on the positive side, so this must mean this is acting like an electrophile. Now for this CO bond here. Now it doesn't necessarily matter when you're looking at polar covalent bonds if it's a single, double, or triple bond. We're just looking at the difference between the elements themselves. Okay, so carbon is more electronegative than oxygen, so that's a partial positive. This is partial negative, so that means this carbon here, right, that's going to be an electrophile. The oxygen is going to be the nucleophile. And then for here, for this carbon-carbon bond here, right, remember there's 4 electrons in that double bond. Okay, and so that's going to have negative character to it. So that's going to result in it being partial negative, and so that makes this a nucleophile. Now for nucleophilicity, okay, so when you're comparing atoms, versions of different atoms, okay, typically it's going to, the negative version of the atom is going to be more nucleophilic than if you have a partial, if you only have a partial negative, okay. So the easiest one to think about is OH minus versus water, right? Water is not particularly nucleophilic, but OH minus is. Okay. So so that's usually good. negative charge is usually better than neutrals when you're looking at the same atom. Okay. Next up, it's a general rule of thumb, okay, that the more basic something is, the better the nucleophile. Okay, so you can look at this, and so, hold up. So if you look at a molecule, if you look at a pKa chart, the higher the pKa value, the better that nucleophile is going to be. So they generally go hand in hand. Okay, and so if you look at, say, these nucleophiles as you're going across, right, you're decreasing pKa's as you're going across, and therefore this is going to be a better nucleophile than this, which is better than this, which is better than this. Okay. And for SN2 reactions, it's all about size. Okay, so but that we need to be able to worm our way into the backside. Okay, and so having something smaller is going to be better. It's just you're less likely to be able to, these groups that are hanging off of it, they're not going to get in the way of being able to go through there. So if you're crawling through a tunnel, right, my little, I had a 5-year-old nephew, he'd be much better crawling through that tunnel than I would be right now. So because he's smaller. Okay? Same thing here. It's all about size with SN2 reactions. So the smaller the nucleophile, the better. Okay. Now there is an issue with polarizability. Okay, this is where things were, I talked to you, you just kind of have to throw everything out. What I just said. Okay, the better the pKa, the better. Well, it's never that easy because there is this issue of polarizability. And this is typically when you're talking about things going up and down the column on a periodic table. So it turns out iodine, even though that it's the worst of the halides, is actually a halfway decent nucleophile. And the reason for that is it's what's called polarizability. And so, again, this is when you're usually comparing atoms in the same column on the periodic table. It's how easy is it to shed solvent molecules. Okay, it's a weird phenomenon. Okay, but it turns out iodine is actually a better nucleophile than fluorine is. Go figure. Something like that. And SH- is easier than OH- because it's not holding on to its solvent shell. So go figure. Now for the leaving groups, okay, on your electrophile, these actually make a lot more sense, okay, because for here what you want to do is you want to have a low pKa on the leaving group, okay, so things that would form a very strong acid are good, right, because what you want to do is you want to have essentially electrophile plus strong base, right, because that would indicate a good nucleophile, to go to product plus weak base. Right? So that's how the reaction is going to want to go. It's going to want to produce a weak base, because otherwise what would happen is the reaction would just go in the opposite direction. Right? If you produce a strong base, that means you've also produced a strong nucleophile, and so that therefore it would be wanting to run backwards. Okay? And so typically strong acids are the ones that are going to give the good leaving group. So the halides, except for fluorine, are really good leaving groups. So I just told you that iodine's a good nucleophile. Go figure. But it's also a very good leaving group, okay, because it has such a low pKa. The halides are pretty good. You can also have these sulfonate ones, which we'll talk about in just a second, as well as water, not OH, but H2O. Right, so because it's really the acidic form of this is actually like that. Being able to release a water molecule is phenomenally great, because what happens is, right, water is incredibly stable, right, which is why it's covering 2/3 of our planet. So it's really, really stable, and so it makes it a great leaving group. Okay, fluorides, not so much, because remember HF is a weak acid, and so fluoride actually doesn't want to part with carbon very often, which is why Teflon is so unreactive. Okay. Now the sulfonic acids. Okay, remember this is very similar to sulfuric acid. It's just one fewer oxygen. So sulfuric acid is obviously a strong acid, so it's sulfonic acid is too. But it just has an organic molecule hanging off of it. Okay, so tosylate is nice because it's for small scale because it has this benzene in it, and so it's easier to visualize. It's really easy to detect. So mesolate's nice because mesolate and triflate are pretty nice because for what is called atom economy, right? Because lots of times these things are designed to get thrown away. We're not throwing away as many atoms. Okay, triflate's really nice because remember back when we were talking about acidity, right? Having electronegative atoms near where the acidic bond is weakens that. It makes it more acidic, right? So if you compare the methyl group to try, 3 hydrogens versus 3 fluorines, right? Now you have these huge inductive effects, which is why you get a lot of orders of magnitude increase in the acidity. And so triflate's a really, really, really good leaving group, okay, because of the presence of these inductive effects from the fluorine. Okay? So negative 14 pK. It's a great one. Now solvents. Solvents are incredibly important for SN1 and SN2 reactions. Okay, and so as it turns out, for SN2 reactions, you want a polar aprotic solvent. Okay, so an aprotic solvent is one where all of the hydrogens are bound to a carbon. Okay, and so acetone and DMSO, right? This is where the hydrogens are. Right? There are not any hydrogens that are not bound to a carbon, right? So even here, so if you have a protic solvent, however, you have at least one hydrogen that's not bound to carbon. You can have them, right? There's a nice one right here on acetic acid. This is a classic protic solvent, right? It has hydrogens bound to carbon, right? But it has at least one that's not, right? So it has this guy here, and alcohols. Well, water has 2, right? Okay. Amines have 2 as well. So you have to have at least one. Okay. The problem with protic solvents is that they stabilize the molecule, which seems weird, but there's a couple things. One, they can bind the nucleophile so tightly through a hydrogen bonding network that they can basically shackle it, okay, and so that it can't get to where it needs to go. It can't get to that electrophile. The other thing is it could actually react with because remember, good nucleophiles are also good bases, so it can also react with the nucleophile or with the solvent. Okay, so you have an issue, but for aprotic solvents, notice you have this issue of some steric clashing here. Not so much when it's binding the cation, but when you're trying to get in here, remember you've got these 2 CH3 groups here. Those are going to provide some steric clashing. Okay, so they can't. So if something like this is acetone, so something like acetone can't get to the negative charge nearly as easily because those methyl groups are in the way. Okay, and so what happens is it kind of digs itself into a hole. Okay, so if you're trying to get to the fifth story of a building, right, and you got to walk up the stairs, it's one thing to start from ground level, right? It's another, to walk up those 5 stairs. It's another thing to start 2 floors in the basement. Okay. And so that's what's happening is you still have to get to about the same height in the activation energy. But because everything is so stabilized, this activation energy is higher, right? So now it's starting at a much lower point, okay? You are, right? So it's actually a bad thing. Not that the reactions won't work, it's just it's going to take a lot more work for it to happen. Okay? And so if you switch to a product solvent for an SN2 reaction, it's going to go much easier, much more easily. Okay? Now for the electrophile, okay, again, remember for SN2 reactions, it's all about size. Okay, so what we want to do is we want to have as little stuff possible where that leaving group is. Okay, so having a methyl bromide is fantastic. Okay, because it reacts with just about any nucleophile. Okay, which is good chemically, but bad for toxicity because it doesn't care what it puts that methyl group on, whether it's, you know, your compound or your DNA. Right? Some of that. So these things can be quite nasty to work with. So you have to be really careful. But for the most part, we're going to be working with primary halides. Okay, so this is the carbon that's holding onto the leaving group is a primary carbon. Right? That means you've got two hydrogens around here and another group, and so it's going to be as easy as get. Secondaries aren't so bad, so they will work. They're just going to be a lot slower than primaries. Tertiaries basically are never going to work. Okay, it's too difficult for the nucleophile to push these three, at best, the three methyl groups out of the way. So it's just not going to work. Okay, because it's just too congested around the carbon that needs to get attacked. Okay, so what you're looking for is you're looking for primary leaving groups and primary carbons. Okay, and again, it's all about size and sterics and being able to get in there. It just takes a lot more energy to get those big groups out of the way, and so the activation energy is huge. Now you have to be careful because all of these are actually primary halides, right? However, this one is going to be really, really, really slow because it has this giant T-butyl group here. Okay, so even though it is primary, it has a huge group next to it. So it's still going to be really slow because it's got to push this giant group out of the way. Okay, so that again, it's got to move all of those, and so it's going to be really slow. Okay, so it's never as cut and dry as anything in organic chemistry. But in general, primaries are going to be better than secondaries. And tertiaries are never going to work for an SN2 reaction. The other thing that's absolutely never going to work for an SN2 reaction is if that leaving group is on a double bond. It doesn't matter if it's an alkene or if it's on a benzene. It's on a double bond, so it means it's never going to work. That reaction is never going to work. Okay. So if you're looking at this one, which one would be better? Right? Well, okay. So for this top one, right. So here's the nucleophile, right. So it's going to be reacting here. Oop, negative. Positive, right? And so we're going to make that bond. It's a secondary leaving group. So that's not fantastic. That's not very good. Okay, and you've got a fairly big benzene group here on the nucleophile, so it's not great. For this one down here, right here is where the nucleophile is, right? And it's smaller than that. However, here you're part of this. The leaving group is directly on the double bond. So no matter how bad this is, this one is never going to work, right? Because the bromine is on the double bond, so it's never going to work in an SN2 reaction. If you try to get this to go, you're going to have to use a different way of making it. You can't use an SN2 reaction. Okay? So it's this top reaction that's going to be the one you want to go with. Now for SN2, biology uses this all the time, okay? And it uses it, one of the best ways I've seen to do it is to use S-adenosylmethionine, okay? This part of this fancy looking molecule is just simply a leaving group, okay? It's the equivalent of a bromine, okay? So this, right? So this nitrogen here is going to make a bond with this carbon, okay? And it just pushes this leaving group away to get back to this molecule here, which can then go back and gets recycled, right? Because nothing in biology, very little in biology is wasted. Okay, and so this, if you look at something like this, it's just simply an SN2 reaction. They'll be, pretty basic. Okay. So even though the molecules look really complicated, that's all that's going on here. Mother Nature's a really good chemist. And if for no other reason, organisms make some amazingly complex molecules. For that. But one of the advantages Mother Nature has is Mother Nature knows all the rules. We don't necessarily know all the rules. We're getting there, but we don't know them all. So, okay. Now SN1 reactions. Okay, so remember, when we think about the SN2 reaction, what's happening is the nucleophiles coming in, and then the leaving group is leaving. Okay, it's this concerted reaction. What's going to happen for an SN1? It's still a substitution. We're gonna substitute our nucleophile where that leaving group is, but we're gonna change the order of events here. Okay? What's going to happen first is the leaving group leaves. Okay, and what's going to be replaced with is electrophile with a positive charge, because it's going to take the electrons with it. Then the negatively charged nucleophile is going to come in and attack. Okay, to make the bond, right? Because you've got something negative, you got something positive, you're going to make a new bond. Okay, but this one has actually two distinct steps. So this is actually the rate determining step, this first one. It only has one molecule in it, so that's why it's considered a unimolecular. But it still uses a nucleophile, it's still a substitution reaction, but the rate determining step only uses one of the two starting materials. And so that's why it's called an SN1. Okay, so SN2 reactions happen in one step, one big concerted step. SN2 reactions actually happen in two steps. The first one is, for the ones, first thing that happens is leaving group leaves. Okay, it's just gonna break apart. It's gonna say, I'm out of here. Whoop. Okay. So you're gonna get this intermediate here. And then your nucleophile is going to come in to make your product. Now for this one, it's a water molecule coming in, and then we just need to come in and deprotonate it, and so we end up with our product here. So there's an extra step because we got to get rid of that extra hydrogen. But this is the basic mechanism here. The leaving group leaves, you're going to make a carbocation, and then the nucleophile comes in. Okay, but for here we have a distinct intermediate. It's not concerted. Okay, remember the second step is the nucleophile attacks. Okay. So for here we have an intermediate. Okay, a carbocation intermediate is formed, and so we have these two little humps with an intermediate, with a sort of a rest area in between. Right? So get rid of that. Okay. But there's two. But the first step of this reaction is going to be rate determining. So because of that, that means that the rate is only determined by the concentration of the electrophile. Okay, it does not depend on the concentration of the nucleophile, right? It's waiting around. The nucleophile is waiting around for this first step to occur. Okay, so it doesn't matter. You can put in 1,000 molar of the nucleophile. It's not going to make the reaction go any faster. And so that's one of the things you can do is if you double the concentration of the electrophile and double the concentration of the nucleophile, if you double both of them and you run the rate would actually only be increased by twofold, right? So that's a good way of telling if you're running under SN1 or SN2 conditions, is if you double the rate of both of them, is the rate just twice, or is it 4 times faster? If it's 4 times faster, hey, you're running under SN2 conditions. If it only goes up by 2, then you're running under SN1 conditions. Okay, so it's a good way to figure that out. Now, one of the implications for this is that, remember, when the leaving group leaves, you make a carbocation. The carbocation is actually sp2 hybridized. And so what happens is, if it's pointed like this, when it becomes a carbocation, it goes flat. Okay, so now there's no reason why the nucleophile should prefer one side or the other. So half the time it comes in from the top, the other half it comes in from the bottom. And so the implication for that is you've lost any stereochemical information that you had before. Okay, so remember, for SN2 reactions, right, you get in this inversion. For an SN1, you get both. You get a racemic mixture. Okay, because you're either going to get it coming in from the top, or you're going to get it coming in from the bottom. Okay, so you're going to get the R and the S. No matter what you start with, you're going to get both the R and the S version for this. So if you're running under SN2 conditions, right, here's our nucleophile, right? Figure out the nucleophile and then figure out where it's going to attack, right? Here's the polar covalent bond here. So that means you're going to attack here, right? There, push this away. But since it's an SN2, you invert. If you're running under an SN1 condition, right, the first thing that happens is the leaving group leaves. And so you're going to get this. And so your leaving group can either come in from the top to make this, or it can come in from the bottom and make that product underneath to make that product. So there's no preference on which way it's going to go. And so you're going to get both. You're going to get this racemic mixture. Of R and S, no matter what you start with. So for an SN2 reaction, if you start with the R, you make the S. If you start with the S, you're going to get the R. For an SN1 reaction, it doesn't matter if you start with R or S, you're going to get both products. Now, the factors affecting SN1 are actually different than what the SN2. Because remember, the rate determining step is the formation of that carbocation. So any way that we can stabilize that, the better. Okay, so what we really want to do is to be able to stabilize this. But again, leaving groups that are good for SN1 are also good, are going to be the same ones that work well for SN2 reactions. Leaving groups are leaving groups. We want the same characteristics for both. Okay. The solvent effects, however, are different. Okay. For SN1 reactions, remember, it's all about stabilizing that carbocation, and so by running this in a polar product solvent, we can stabilize that carbocation. Right. The same thing that was being difficult with that was problematic with an SN2 reaction actually helps us in an SN1. You can make a hydrogen bond to that carbocation to help stabilize it, so it's more likely to form. Okay, so for SN1 reactions, we want polar product solvents because the solvent will help stabilize it. Okay. So, and you can see this here, so water, methanol, ethanol, things like that, these polar product solvents work really, really well. If you run it in an A product solvent, like diethyl ether, or even hexane now, hexane is non-polar, so these are going to be really, really, really slow. Now, I'm not going to make you predict which one is which, but what I'm going to predict is, what I would tell you is, if you're running this under SN2 conditions, which solvent class do you want? Well, I want it to be a polar product solvent. Okay. So one of the things is that
though, because these reactions are typically slow, okay, you can actually have these things, you can actually have the solvent can sometimes actually react with the molecule, and this is what's called solvolysis. Right? So your solvent is doing the reaction instead of your nucleophile. So if you're running this in water, right, you're trying to do this. So even if you put a different nucleophile in here, what can happen is the water can come in and attack, and that ends up being that becomes your nucleophile instead of the one that you want. So you do have to be careful about the solvent type. Okay, so if you're so just be careful. So sometimes you have to tune it. Okay, so if you have a mixture, so lots of times what you have to do is you have to run these in dry solvents, right? So because if you have any water around, so it's hard to do it, say in the around here, doing in the south, it gets really hot and humid in the summer. So that means there's a lot of water in the air, and so for a lot of the solvents you have to be really careful that they don't absorb water, because let's say you wanted to do this reaction where you only had methanol. Well, if your reaction's a little wet, there's a little bit from absorbing it from the atmosphere, you can get some of this product as well, where the water will from the atmosphere will come in and react. So you have to be careful. So again, the other thing is, right, so for the electrophile, okay, we want obviously a good leaving group, but what we want to do is we want to have this actually have the leaving group be on a tertiary carbon, right? Because again, it's all about stabilizing the carbocation. So tertiary carbocations are way more stable than secondary or primary. Okay, secondaries aren't so bad. Primary is never going to work. Okay, so about that, and so we've flipped it on our heads from SN2. So for SN1 reactions, we want tertiary leaving groups on tertiary carbons. On SN2, we want them on primary carbons. Okay. The other thing that helps is having adjacent pi bonds. Okay, whether that be carbon-carbon bonds, carbon-carbon double bonds, carbon-oxygen double bonds, things like that. This can really help because once the carbocation is formed, we can then use resonance to stabilize it. Okay, so if you're able to stabilize it, it's more likely to happen. Okay, so being adjacent, not on a double bond, right? Because for that one, remember, we can't really have that thing go away, because the leaving group isn't going to leave. Just like with an SN1 reaction, we don't want it on the double bond. We want it next to it so we can do a resonance structure. Okay. So if it's on a double bond, it can't work because the orbitals are misaligned. Okay, so the pi bond of the carbon-carbon pi bond is like in the plane of the board. If the leaving group is, say, on a wedge here, the orbital is actually going to be coming out at you, so they're not aligned properly. They're what's called orthogonal, so they're 90 degrees away from each other, so the carbon-carbon pi bond can't help out. Okay. So, but if it's adjacent, no problem. It can rotate to be able to get aligned. But if it's fixed like this and it's 90 degrees, not going to work. So on a double bond, bad. Adjacent to a double bond, that's awesome for running an SN1 or SN2 reaction, actually, as it turns out. Now, so one of the problems with SN1 reactions, okay, is that you're forming that carbocation, right? And while it's waiting around for that nucleophile to come in and get rid of it, it can rearrange, okay, in order to stabilize that, stabilize the carbocation. These reactions are fairly slow, so it has some time to sort of saying, well, if you're not going to stabilize it, if you're not going to get it rid of it, I'm going to stabilize it to help me out. Okay, and so what can happen is, so if you have say a secondary carbocation, what we can do is we can move a group over, either a methyl group or say a hydrogen over, a hydride shift. And so what's happening is, look, we're going from a secondary carbocation
to a tertiary. That's way more stable from the from the molecule's point of view. Okay, and so what's going to happen is you will get these shifts. Now it does cost energy. Okay, so it would prefer to move a hydrogen over than a methyl group. It's the same reason why would you rather move a 20-pound suitcase or a 100-pound suitcase, right? It's just the methyl group is just way heavier than a hydrogen, so so it's going to be easier to move the hydrogen, but it still can move a methyl group if need be in order to form this, and it needs to be immediately adjacent to it. Okay. And if it doesn't do you any good, right? If it were to form just a regular, if you would go from secondary to a secondary, well, it's not going to do you any good. So the molecule won't spend the money. But if it can, it'll spend a little that energy to move the group over if it gets a big benefit at the end, right? So if it has to spend that dollar to win $2, right, in the lottery. Okay, so here we go. So would a methyl or hydride shift to make this molecule more stable? Okay, and so we have two options. Okay, so we have so let's say, okay, so we have formed this carbocation here, right? And it's secondary, right? Because it has two, the carbon has two other carbons on it, right? Not too bad, right? So if we were to shift this methyl group over, okay, what would happen is we would get this. I'm going to do this in blue so it's easier to see. And then that would mean that this carbon has the positive charge, right? Because it only has 3 bonds, right? But the problem is, if we look at this, this is also secondary. So it doesn't do us any good. Okay? So let's try this again. But instead, let's move that hydrogen over. Right, so let's move, hold up. There's a positive charge right there. Okay. So let's move that hydrogen over. We move the hydrogen over there, so we end up with this. Now the carbocation is there. And so for here, now it's 1, 2, 3. Now it's a tertiary carbocation. That's much, much, much more stable. So what we're going to want to do is, so what this molecule is, in order to be able to stabilize itself, it's going to want to move a hydrogen over. Okay, in this case, because in doing so, you're taking that carbocation from a secondary to a tertiary. So that's much better for the molecule. And so then if the nucleophile comes in and sees it, it's gonna, when the nucleophile comes in, it's going to see this version of the molecule. So the nucleophile is going to come in and attack here. So if you have a nucleophile, it's going to come in and attack here because this is the only one that this is the only version that it sees. Okay, to make the product. So you can actually get this going, and so this I always thought was really cool, is you can actually build this in, and so what happens is this bond here gets shifted to here, and so that becomes there, and so you can actually pop open a ring, stuff like that, and by doing so, it actually, you go from a secondary to a tertiary. You also go from a 4-membered ring to a 5-membered ring. It also relieves ring strain. Stuff like that. And so you can actually, if you want to build these 5-membered rings, this is a really good way of doing it. Start with a 4-member and pop it open. You plan that hydride shift, a shift, or actually in this case it's a carbon shift,
into the synthesis. So sometimes you can do this. I'm not going to make you do this because even graduate students have problems looking at ring openings with that, but they are really cool. So when you can plan them in. Now for SN1 versus SN2, okay, remember they're looking at totally different. They are, while they're both substitution reactions, their preferences are going to be completely different, right? Maybe for SN2, we're looking about everything has to do with size. With SN1, everything has to do with stabilizing that carbocation, right? So if you're running a tertiary, if your leaving group is on a tertiary carbon, then it's too big. So, but the carbocation that's formed is very stable. So there you go. It's going to want to do an SN1 reaction. If you have a primary carbon, primary carbocations are really unstable, so they're unlikely to form. So SN1 reaction isn't a good option, so you have to run it under SN2. Now for secondary, it's sort of one of those. There's a bunch of other like little considerations. Okay, so it really has to do with how well it can stabilize, how poorly it can stabilize, how big the nucleophile is. They get really messy in a hurry. So. Okay, but also for SN2, they prefer aprotic solvents, and SN1 prefer protic. Okay. And so here's a nice little summary chart. And I think that's it. Okay. Good luck.